Okay, to help you with these, a lot of people are substituting in a variable to represent the trig part of this equation. So if you let a equal sine x, then I can rewrite this as 2a squared minus a minus 1. And then it's a little easier to factor at this point. So factoring this, I get 2a, I'm going to get a minus 1 there, and then a plus 1. Because I know I have to get a minus a here. If I distribute, I would get a minus 2a plus 1a would give me a negative 1a. So those are my two answers there. I set each one of these equal to 0 to find my two answers, and then here I would get 2a equals negative 1 divided by 2, and then you get negative 1 over 2. And over here, one step, a equals 1, but knowing that a equals sine of x, I'm going to substitute back in. When does sine of x equal negative 1/2? I'm going to get two answers for that. Negative 1/2, two answers here, 7 pi over 6 and 11 pi over 6. So those are the two answers for this. And then here, if I let sine x equal 1, that's going to happen at exactly one place up here when x is pi over 2. So looking at my domain, I only have to worry about these three solutions for this problem. This next problem, I'm going to do the same thing. If I let a equal cosine, then I'm going to get a plus square root 3 equals negative a. So when I bring this a to this side, I'm going to get 2a plus square root 3 equals 0. Bring the square root 3 to this side, then divide by 2, and you get that. Plugging cosine back in, I get cosine of x equals negative square root 3 over 2. Looking at my unit circle, that's going to happen in two places, here and here, because cosine is negative square root 3 over 2 over there. So that's 5 pi over 6, and then 7 pi over 6. My two answers on 0 to 2 pi, but if I need to look at all of them, I need to take each one of these, and I am going to get another solution every 2 pi after this. So take 5 pi over 6, add 2 pi times k. And down here, the same thing, 2 pi times k. Just multiples of 2 pi. This one, let's let a equal cosine of x again. So then I would get 2a squared minus square root of 3 times a equal to 0. This is an easier problem where I can just factor out an a, and what I'm left with is 2a minus square root of 3. And in each case, I'm going to set a equal to 0. So a equal to 0, and this term also equal to 0. So here, I don't have to do any work over here, but here I do have to move square root 3 over here, then divide by 2, then plug in cosine back into both of these. When does cosine equal 0? That's going to happen two places. Cosine equals 0 here and here. Pi over 2 and 3 pi over 2. Cosine equals square root of 3 over 2 here and down here. So at pi over 6 and 11 pi over 6, those are my 4 solutions on 0 to 2 pi. Last one, this one, again, I'm going to let a equal sign. That would get me 2a squared minus 1. Bring the 1 over, or equals 0, bring the 1 over, I get 2a squared equals positive 1. Divide by 2, I get 1/2. And I take the square root, and I get square root of 1/2. But in this case, if I square some number, I can either do plus or minus in order to get a 1/2. So when you're taking the square root, you are taking plus or minus the square root. Right now, square root of 1/2 doesn't look that familiar, so I'm going to simplify this. The square root of 1 is just 1, square root of 2 down here. Also not the most familiar, so I rationalize the denominator, square root of 2 over square root of 2 with a fancy 1, and then I end up getting plus or minus square root of 2 over 2, which is a lot more familiar. So when does sine equal plus and minus square root of 2 over 2? That's going to happen in several different places. Sine equals positive square root of 2 over 2 up here, here and here. And then down here it's going to be negative square root of 2 over 2. So I'm going to have 4 solutions here, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And the tricky part here is for all solutions. Now you might think, well, that means I have to take this and do plus 2 pi k, but the nice thing about this situation is that I'm going to get a solution every pi over 2 rotations. So every pi over 2 radians, a quarter of the circle, I'm going to get another answer. So from here to here, here to here, here to here, and then here to here, each one of those is just another plus pi over 2, which means that I can represent all of these solutions, even on negative infinity to infinity, as simply pi over 4 plus multiples of pi over 2. So pi over 2k, basically.